Imagine holding two coins, spun together in a special way. You give one to a friend who travels to the other side of the world. The moment you look at your coin and see its heads, you instantly know, without a shadow of a doubt, that your friend's coin is tails. This isn't magic. This is the strange and wonderful reality of quantum entanglement. Albert Einstein famously called it spooky action at a distance. It's a ghostly connection between two particles, where the state of one is intrinsically tied to the other, no matter the distance separating them. This bizarre feature of the quantum world has been proven time and again, earning a Nobel Prize in 2022 and powering the next generation of technology in computing and cryptography. But for all we knew, this phenomenon was a feature of the low-energy microscopic realm. What would happen if we looked for it in the most extreme high-energy environment on Earth? Enter the Large Hadron Collider, the most powerful particle accelerator ever built. Here, deep beneath the Swiss-French border, scientists at the ATLAS and CMS experiments have made a landmark discovery. For the first time, they have witnessed quantum entanglement at the highest energies ever recorded, and in a completely new system, the top quark. The top quark is the heavyweight champion of fundamental particles, so massive that it decays almost instantly. This fleeting existence makes it a perfect, pristine laboratory for studying quantum properties before the universe has a chance to interfere. The teams at the LHC sifted through petabytes of data from proton-proton collisions, looking for pairs of top quarks born together in the fiery aftermath. The theory was simple. If these quarks were entangled, their spins, a quantum version of angular momentum, would be linked. Since the quarks decay too fast to see directly, the scientists did something clever. They measured the directions of the particles that the quarks decayed into. The angle between these decay products held the secret, and the secret was revealed, with a statistical certainty that leaves no room for doubt. Both the ATLAS and CMS teams confirmed it. The top quarks were entangled. Their spins were locked in a cosmic dance from the moment of their creation. The CMS collaboration pushed the boundaries even further. They found entanglement even between quarks flying apart at tremendous speeds. The distance and time between their decays were such that no classical signal, not even one traveling at the speed of light, could have passed between them. This was pure, unadulterated quantum spookiness, playing out at an energy scale 1 trillion times higher than your typical tabletop experiment. So why does this matter? Because it opens an entirely new window onto the universe. As CMS spokesperson Patricia McBride puts it, we can now test the standard model of particle physics in new ways. We have a new tool. By measuring entanglement in this high-energy playground, we can search for tiny deviations from our predictions, cracks in our current understanding that could point the way to new particles, new forces, and a deeper theory of everything. This discovery doesn't just confirm what we know about the quantum world. It forges a new link between the very small and the very powerful, and it gives physicists a rich, new menu for exploration. The spooky action Einstein once puzzled over is now a fundamental probe, helping us unlock the deepest secrets of our universe. What if I told you a computer just solved a problem in under 5 minutes that would take the fastest supercomputer on Earth 10 septillion years? That's a 1 with 25 zeros after it, an age far longer than the universe has existed. This isn't science fiction. This is the reality of Google's new quantum computer chip, nicknamed Willow. But this incredible achievement has sparked a debate that goes far beyond processing power. It's forcing scientists to ask a mind-bending question. Did this computer prove the existence of parallel universes? The idea comes from Hartmut Neven, the founder of Google's quantum AI team. He argues that the only way to explain this impossible speed is to embrace one of the most bizarre ideas in physics, the multiverse. This theory, pioneered by physicists like David Deutsch, suggests that every time a quantum event happens, the universe splits. Every possible outcome occurs, each in its own separate, parallel reality. Deutsch proposed that a quantum computer isn't just working in our universe. It's so powerful because it's outsourcing the computational work to countless versions of itself across these other universes, then bringing the answer back to ours. When Nevin saw Willow's performance, he claimed it lent credence to this very idea that quantum computing is a direct window into the multiverse at work. But here's where the story splits into two universes of its own. Many physicists are pushing back, hard. Critics, like scientist Ethan Siegel, argue that this is a huge leap. They say you don't need to invoke parallel worlds to explain quantum mechanics. The counter-argument is that the strange phenomena that power quantum computers, like particles existing in multiple states at once, are simply a fundamental mathematical property of our one universe. They claim Nevin is mistaking a complex mathematical space for a physical reality teeming with alternate worlds. Furthermore, they point out that the problem Willow solved, called random circuit sampling, is a custom-built benchmark designed to show off a quantum computer's strengths. It doesn't have a practical application yet, and there's no direct, physical evidence of other universes in the data. The link, they say, remains purely philosophical. So what does Willow's achievement really prove? One thing is certain. It marks a monumental leap forward in quantum computing, demonstrating a power that is truly beginning to defy classical imagination. It shows we're getting better at controlling the fragile quantum world, which could one day revolutionize everything from medicine to material science. But has it proven the multiverse? The honest answer is no. For now, it remains a tantalizing, unproven theory. Perhaps the most important takeaway is the debate itself. These incredible new machines are no longer just tools for solving problems. They are becoming instruments that force us to confront the deepest, most fundamental questions about the nature of reality. And in our universe, that's a conversation that is only just beginning.